Hi everyone, we're going to go ahead and go over the IMFs for each of the solvents that were used in the Crayon demo today. So that's water, turpentine, hexane, ethanol, and acetone. Now, the easiest one that we can talk about is the fact that every single molecule, every single atom, anything that's made up of matter is going to have electrons. And if you've got electrons, then you've got the IMF LDF, or London dispersion forces. So it doesn't matter if the molecule is polar or nonpolar, but every single one of these is going to have at least an LDF. So I'm going to go ahead and add that to each of my lists for all of these solvents. We know that these are molecules, and all molecules have some sort of intermolecular forces, at the very least, London dispersion forces, or LDF. Okay. All right, because they all have electrons, and it's talking about the dispersion of electrons. So we're going to start with the easiest one, in my opinion, and that's hexane. So here's hexane. Hexane has 6 carbons and a bunch of hydrogens around it. The way we're going to figure out whether this has anything in addition to LDF is we have to calculate bond polarity. And to calculate bond polarity, we have to look at our electronegativity values. Okay, so I went ahead and already kind of looked up the different electronegativity values, and they're going to be written like this on our screens. So we need to find the difference between every single bond, and it looks like we only have carbon bonded to hydrogen in this entire molecule. So I'm going to take 2.55, which is the electronegativity value for carbon, minus 2.10, and that's going to give me 0.45. Okay, 0.45. We then use that difference to help us figure out what type of bond we're working with. 0.45 puts us right here, which is in the nonpolar covalent. So these bonds, all of these bonds, are nonpolar bonds. And because we have all nonpolar bonds, that makes this a nonpolar molecule, which means we can't have dipole-dipole. And we can't have H bonding because we don't have any hydrogens that are bonded to F, O, or N. We don't have that. So hold the phone, it's not here. So we can't have H bonding. So the only type of intermolecular forces for hexane are LDF, which I will just leave here. So that's our final answer for hexane. Now we're going to go on to what I think is the second easiest, and that's turpentine. Turpentine, if we look at this, it's made up of all carbon and hydrogen bonds. There's also carbon-carbon bonds, but we know that carbon minus carbon on the electronegativity scale is going to give us 0, right? And that 0 puts us at a nonpolar covalent bond. So carbon to carbon is nonpolar covalent. We also have carbon to hydrogen. We know that that is also nonpolar covalent. So all of these are nonpolar bonds, okay, which means that this is a nonpolar molecule. Okay, now we don't have any, so we know that we're going to have at least LDF, but we don't have any polarity, so it can't be dipole-dipole. And because we don't have H bonded to the phone, F, O, or N, we can't have H bonding. So the only type of intermolecular force that turpentine experiences is going to be LDF. Notice that they're only made up of carbon and hydrogens, so a good tip is that if they're made up of carbon and hydrogen, they only experience LDF. All right, the next one we're going to go ahead and talk about is acetone. Acetone has a bond from oxygen to carbon, and then it has a bond from carbon to hydrogen. We know that the difference between carbon and hydrogen is 0.45, so these bonds are going to be nonpolar. This bond from carbon to carbon is going to be nonpolar. But how about this bond between oxygen and carbon? If we calculate the difference, 3.44 minus 2.55, we are going to get a difference of 0.89. 0.89 puts us about here on the electronegativity difference scale, this polar continuum, and that's going to put us at a polar covalent bond. So this bond right here is polar. And I'm going to go ahead and add a dipole because oxygen has a higher electronegativity than carbon. Okay, so we do have a little bit of polarity here, which means in addition to experiencing LDF, ethanol or acetone is going to experience a little bit of a pull, because if we look at this polar bond, we can see that the net sum of all of these bonds is going to be going in this upward direction. So this is a polar molecule. Because it's a polar molecule, that means we experience dipole-dipole. However, because we don't have any H's bonded to F, O, or N, we don't have hold the phone, we do not have H bonds. So the only intermolecular forces that acetone experiences LDF and dipole-dipole. All right, let's move on to a personal favorite of mine, water. So we're going to go ahead and calculate the difference between oxygen and hydrogen to figure out if this bond is polar. That difference is going to be 0.94, which puts us on the polarity continuum about right here. So that means that this is in fact a polar covalent bond. I'm going to go ahead and label my more electronegative atom with a partial negative charge, which means my hydrogens both have partial positive charges. My dipole arrow on the bond is going to go pointing towards the oxygen. Sorry, I know I put those on different sides of the bond, but they are both bond dipoles. And so now we can figure out whether or not this has anything in addition to LDF. We have to figure out if this is a polar bond or a polar molecule. So we know that it's going to be the net sum of all of our bond dipoles, or you could take a look at our VSEPR chart. Water has 2 bonding domains and 2 lone pair domains, and we do have polar bonds. So we can use this last column here to decide whether this molecule is polar or not. And it says here that yes, it should be polar if we have polar bonds, which we do. So now we need to draw our molecular dipole. Think of that tug of war. Where is the net sum of movement? And you could say that it would be going in an upwards direction. So this is a polar molecule with polar bonds. And because it's a polar molecule, it's going to have dipole-dipole. We also have H bonded to F, O, or N. Hold the phone. Because we have that, we know that we're experiencing H bonding. So water experiences all 3 intermolecular forces. All right, so finally we have ethanol. Ethanol looks like this. It's got a lot of different bonds throughout it. We know that carbon to carbon is going to be 0, so that is a nonpolar covalent bond. We know that carbon to hydrogen calculates in at 0.45, so it's going to be a nonpolar covalent bond. We know that oxygen to carbon is going to be 0.89, and that oxygen to hydrogen is going to be 0.94. Now both of these are going to clock in 0.94 and 0.89 about right here. So both of these are polar bonds, which means we have to draw in a bond dipole. So oxygen in both of these bonds is the more electronegative element. So it's going to be labeled as partially negative, which means our carbon is going to be partially positive, and our hydrogen is also going to be partially positive. If we draw in our bond dipoles, they will look like this, pointing towards the more electronegative element. Okay, and you can kind of think of this as like if you just look at this as one molecule like this, just pay attention to what's touching that oxygen. How many electron domains does it have? It has 4. We treat this like water. So we have polar bonds with 4 electron domains, 2 bonding and 2 lone pairs. So that means, yes, this is polar with a net dipole moment. This should really be bent, going in an upwards direction. So this will experience LDF, dipole-dipole, and because we have H bonded to O, it's also going to experience hydrogen bonding. So our final answer is going to be ethanol experiences all 3.